All right, welcome back to another lecture video. Today we're going to be discussing material out of section 4.3 in the textbook. 4.3 deals with what are called the derivative tests, so the first derivative test and the second derivative test. We'll be looking at some examples of applying both and then the applications that they have to being able to sketch curves by hand using calculus. Just to give you a rundown of what we got going on this week, there is an announcement up on the main page here that has all the material for this week. We'll be looking at first and second derivative tests today. Sections 4.3 and 4.5. We'll be covering L'Hopital's rule on Wednesday. That's out of section 4.4. And then we'll start looking at optimization on Friday, and we'll actually spend 2 days on optimizations, which your third CalcLab project is on, optimization. So we'll look at optimization on Friday and then next Monday, and that's section 4.7. You have three things that are due this week. You have quiz 10 on Friday. Quiz 10 will cover the derivative tests and L'Hopital's rule. So you'll have both of these on the quiz on Friday. It does not cover optimization. And then you have two homework sets due, both those due on Sunday. Section 4.3 homework and section 4.4 homework. If you have any questions this week, shoot me an email. Show up to office hours. I'll help you however I can. Sorry I have not graded the exams yet, but I should be working on those later today, and I hope to get them done tonight. But we'll see if I have enough time to do that. All right, so let's just dive into it. Take a look at the derivative tests. There are several derivative tests that we're going to use, the first derivative test and the second derivative test. I'll tell you that these are important enough in the grand scheme of the course that they should be memorized. So you should spend some time to memorize the statements of both of these two tests. You can think of them as being theorems if you like. They're true statements that form the backbone of a lot of the analysis that we're going to do today. So let's start with the first derivative test. The first derivative test says, if you have a critical point, then to determine whether that critical point is a local max or a local min, you need to look at either side of the derivative's critical point. In other words, you need to test values to the left and to the right of the critical point. So if, when you test, the critical point goes from values to the left, so it changes from positive, the slopes are positive to the left and negative to the right, so your function is increasing to the left, decreasing to the right, then what the first derivative test tells you is that at the point C, this point must be a max, and it would have to be a local max. See, the difference between our topic today and the absolute extremes that we looked at last week is last week we were only looking at functions on a closed interval. So we were looking for absolute maximums and minimums. This week, and especially today in this lecture, we're considering a function on its entire domain. So we're looking at minus infinity to infinity, and so we have to determine all of the maximums and minimums. The local ones, we need to look at ending behavior to see if there are some absolute ones, things like that. So if you're going from positive slopes to negative slopes, the point where it changes over at the critical point must be a maximum. Similarly, if you go from negative slopes to positive slopes, then you know that the point where that change occurs must be a local minimum. If the derivative does not change values, in other words, you're positive, then positive again, or negative, then negative again, the point at C is neither a local max or a local min. It could still be an inflection point, though. So we'll have to check the second derivative. Remember, where the first derivative is equal to 0, we call x equal to c a critical point. So you can think of the first derivative test as the critical point test. We're testing on either sides of the critical points. Okay, similarly, the second derivative test says if your first derivative is 0 and you want to know whether that critical point at C is a maximum or a minimum, you can actually determine that not by looking at the first derivative like we did here, but you can actually determine it by looking at the second derivative. So if our second derivative is greater than 0, remember we call that concave up. So if you have a interval on which a critical point is concave up, then that critical point must be a minimum. You know your graph turns up at the point C. It's part of a concave up part of the graph. It must be a minimum. If, on the other hand, your second derivative at the point C is negative, then you know the graph must turn down at C, and so you know at the critical point C you have a maximum. Now here's the thing. If the second derivative, so this is concave down, if the second derivative is also 0, meaning your first derivative 0 and your second derivative 0, then neither of these tests will tell you anything about the point C, and so you'll have to resort to something else. Sometimes your second derivative will be 0 to critical point, but then the first derivative test works. But if neither of these tests work, then you're going to have to resort to something else. You'll have to maybe look at the third derivative or just simply graph it to determine if a given critical point is a local maximum or a local minimum. All right, so those are the two tests that you should commit to memory. We're going to apply them in several different cases. When would you want to use the first derivative test? Well, you're going to use the first derivative test anytime you're asked to find intervals on which the function is increasing or decreasing. Anytime the second derivative is not easy to find, like sometimes taking one derivative is kind of nice, but if you're asked to take two derivatives, that can be quite difficult. If the second derivative does not exist at a critical point, then you're stuck with the first derivative test. That's that inconclusive part here. The second derivative being inconclusive at a critical point, these two things, you've got to use the first derivative test if the second derivative test fails. The second derivative test is most compelling when you're being asked to find concavity and inflection points. Like we said, you can think of the first derivative test as the critical point test. You can think of the second derivative test as the inflection point test. You're going to be testing on both sides of the inflection points of the given functions. All right, this is kind of a breakdown of what we're going to be doing today, the analysis that we're going to be doing. But we're going to take a look at, I think I've got 4 examples planned. There are several more and there's some extra videos that I posted on this, and there's several examples in your textbook for you to take a look at. All right, so let's start with this first example. This is a chance for you to try it out and see if you understand what's going on here. What I have is the function x squared minus 3 times e to the x, and I would like for you to tell me which of the following choices is a correct sign map of the first derivative. What that means is each of these is the first derivative. So the values on here are the first derivative values. And so the idea is, just looking at A says that the function f, its derivative is 0 at negative square root 3 and positive square root 3. So what I'm telling you if you pick A is that the critical points of this function are plus and minus root 3. If you pick B, I'm telling you the critical points are negative 3 and 1. C, I'm telling you negative 3 and 1. D, I'm telling you negative 3, 0 and 1. The point is, only one of these is correct, and then the positive and negatives, what I've done is tested a value to the right of square root 3, say like 2, and I tested a value to the left of square root 3 like 1, and I plugged those into the derivative. Remember, these are derivative values on this sign map, and I determined that the derivative was positive here, negative here, positive here. So B says that the derivative is positive, negative, positive. All right, so based on that, I want you to pause the video for a second, try to work out, figure out what the critical points, and try to figure out which of these is the correct sign map for this problem. All right, if you haven't paused yet, please do so. We're going to take a look at it together. The first thing that you should do is, because this is a derivative test, you should take the derivative. So I'm going to take the derivative here. Bear in mind that this is a function of x times a function of x, so this is product rule. So I'm going to take the derivative of the first term times the second plus the first term times the derivative of the second. So this is our product rule. The derivative of the first term is 2x. The derivative of the second term, the derivative of e to the x is just e to the x. And if you simplify this result, you get this derivative. So critical points are where the derivative is equal to 0. So I'm going to set this equal to 0. I know e to the x can never be 0. Exponentials do not take on the value, y value 0 anywhere for any x. So I need this guy, this polynomial, quadratic, to equal 0 in order for this thing to zero out. So if we set x squared plus 2x minus 3 equal to 0, it looks like it factors into x plus 3, x minus 1. So the two critical points are x equal to negative 3 and x equal to 1. So here are my critical points, which means that the correct answer is either B or C. Now, all I'm doing is testing values in the derivative, okay? So what I would do is your derivative here, once it's factored, is x plus 3, x minus 1 times e to the x. So this is what your derivative looks like once we've factored this piece. So imagine taking a value to the right of 1. So imagine taking 2. If you plug 2 in, 2 plus 3 is 5, so it's positive. If you plug 2 in, it's positive. If you plug 2 in, it's positive. All three factors are positive, so the derivative with 2 plugged in is positive. So the point to the right of 1 should be positive in sign. So picking between B and C, B is the correct answer. Let's just take it a little bit further and also test between negative 3 and 1. So let's test 0. If you plug 0 into the derivative, you get positive, negative, positive. So that's a negative sign. So the second derivative would be negative. Or excuse me, the first derivative at 0 would be negative. And the reason I know every point in this interval is also negative is the derivative can only change values once it hits 0. Right? If you have negative slopes, those slopes don't become positive until you pass through 0. So 0, finding where the slopes are 0 is important because it separates the interval or the domain of the function into intervals where you're either increasing the whole time or decreasing the whole time. So I know here this is negative. If I was to test to the left of negative 3, so pick a value like say negative 4. If you were to plug negative 4 in, that term would be negative, that factor would be negative, that would be positive because exponentials are always positive. So a negative times a negative is positive times a positive is positive. So I know that I would have a positive slope over here. The point to this is I know my function is increasing on this interval, decreasing on this interval, and increasing on this interval. So B is the correct answer. If I was to ask you what are the intervals of increasing and decreasing, remember we're on the entire domain of the function, so minus infinity to infinity. This function is increasing if you are to the left of negative 3. So you would write that negative infinity up to negative 3, or it's also increasing from 1 to infinity. Where is the function decreasing? Well, the function is decreasing between negative 3 and 1. So if you look, we have described every point between negative infinity and infinity where the function's increasing or decreasing. Notice we didn't include negative 3 because the slope is 0 at negative 3, so it's neither increasing nor decreasing. And we didn't include 1 because it's also a critical point, which means at that point the derivative is 0, it's neither increasing nor decreasing. But these are all the points where the function is increasing or decreasing. Now let's talk maximums and minimums. You can see here that we go from positive slopes to negative slopes, which means the point at -3 will turn out to be a local maximum. Similarly, you go from negative slopes to positive slopes, so you know the point at 1 will be a local minimum. And that's where we're applying the first derivative test. The first derivative test allows us to say that. So our local max, or maxima is the plural here, our local maxima occur at x equal to -3. And then what you would do is you would plug -3 into the original function right up here. Let's see, what would that give you? -3 squared is 9, minus 3 is 6. So this would give you 6e to the -3 would be the local maximum value. And similarly, for the local minimum, you do the same thing. We know the local minimum is at, let's see, x equal to 1. It's hard to see that 1. So at x equal to 1, we have a local minimum. And if you plug 1 into the original function, 1 squared minus 3, so 1 minus 3 is -2. E to the 1, or -2e. So there's my local maximum, local minimum. These are given to us by the first derivative test. So this is the gist of what you're going to go through. We're going to do a more in-depth example next, but if you're going to apply first derivative test, you take the derivative and find the critical points. You then create a sign map, just like I have here, where you're going to map out whether the derivative is positive or negative in different intervals. Once you have that, you can list your intervals on which the function is increasing and decreasing, and using the first derivative test, determine if there are any maximums or minimums anywhere on minus infinity to infinity. All right, so let's take a look at another example. Here we're going to determine intervals on which the function is increasing, decreasing, and concave up, concave down. So we're using both first and second derivative test. So this is a complete start to finish example here. Since I'm using both first and second derivative test, I need to calculate both the first and second derivatives. So we'll start with the first derivative. Notice that quadratic, all of those share a factor of 3, so I'm going to pull that out. And it looks like it'll factor into x minus 5, x minus 1. So you've got two critical points here. At x equal to 5 and x equal to 1. All right, second derivative. So what I'm looking for when I calculate the second derivative is just here's the first derivative. I'm just going to differentiate this one more time. So the derivative of 3x squared is 6x minus 18. So 6x equals 18, or x is 3. This is a place where the second derivative is equal to 0. So we call this an inflection point. Now once you have your critical points and your inflection points, what I would recommend is drawing a timeline here, or a number line, and plotting all the points that you found. So from left to right, smallest to largest, plotting the points, giving yourself some room in between. So x equal to 1 is the smallest. So x equal to 1 is going to go right here. It is a critical point, so I'm going to draw a dotted line above, and I'm going to put 0 at the top of it because I know the derivative has value 0 at x equal to 1. Similarly, x equal to 3 is next. So I'm going to write down x equal to 3. I'm not going to draw a line above it because this is where I'm going to do my mapping for my first derivatives. I'm going to draw a line below it. I'm going to do second derivatives below the line. So I'm going to draw a line down, second derivative, and I know this is where the second derivative is 0 because it's an inflection point. Finally, I'm going to take x equal to 5, jot it down, and draw the line up because it is a critical point, so it's where the derivative is 0. So everywhere in the top part of this diagram, I'm going to be looking at values of f prime. In the bottom half of this diagram, I'm going to be looking at values of f double prime. So we'll start in the top, and I'm just going to simply pick a point in each of these three regions, test them in the first derivative, and determine if they're positive or negative. So pick a point to the left of 1. I'm going to pick that point to be 0. So if you plug 0 into the first derivative, f prime at 0 turns out to be 15, which is positive. I don't care about the number, I just care whether it's positive or negative. So if the derivative is positive there, I know I am increasing, and that's usually what I draw in to represent increasing. Okay, next we'll pick a value between 1 and 5. I can choose 3 if I want to, because 3 is not a critical point. I can choose any value between 1 and 5, any value in this region. So yeah, let's just do 3. If I calculate the derivative at 3, so plugging 3 into each of these factors, it's negative there, positive there, so overall it looks to be decreasing in this interval. And then pick a value to the right of 5, let's say 6, so I'm going to plug 6 into my derivative, and that's positive, so overall this is positive. All right, so by the first derivative test, I have increasing to decreasing, which means this guy has to be a max. So I'm just going to draw that up there. We have a maximum at x equal to 1. Here we go from decreasing to increasing, so we have a minimum at x equal to 5. Now, I was able to determine that based on the first derivative test. What if I had used the second derivative test? Well, the second derivative test says, take your inflection point, which we did. That creates, in this case, 2 regions. The critical points fall on those regions. Test the second derivative at the critical point. So I'm going to test my second derivative at x equal to 1. So if you plug, so here's the second derivative right here. If you plug 1 into the second derivative, you get negative 12. So this is negative, which means that the function is concave down, which means that the point where it turns at a maximum point. You can see that lines up with what we got here. So this would be using the second derivative test. We know at x equal to 1, we have a max. Similarly, I can test over here at the critical point 5. And if I plug 5 in, I get 6 times 5 is 30, minus 18 is 12. So that's a positive second derivative. So I know we're concave up over here. And by the second derivative test, any critical point, any turning point that occurs must occur at a minimum. So I know I have a minimum by the second derivative test, which matches what we got with the first derivative test. So this is a complete diagram at this point of all of the information you might be asked on this kind of question, and it really just falls to you at this point to write it down correctly once you have it diagrammed. So where is the graph increasing? Well, the graph is increasing from negative infinity up to 1, and then again from 5 to infinity. The function is decreasing from 1 to 5. The function is concave up. So looking at its second derivative, concave up over here. So that's from 3 to infinity. And the function is concave down from negative infinity up to 3. Okay, finally, the last little bits of information are local maxes and mins. We have a local max here at the point x equal to 1. So at 1 comma whatever the y value is, 1 f of 1. We have a local minimum at the point x equal to 5. 5 is where our minimum is. So that's 5 f of 5. Now, once you've completed all this information, what you should always do is check yourself in something like Desmos. So if we were to plot this graph in Desmos, So I'm just getting a good window for y'all to look at it here. All right, so if I pull this over real quick. So here is the function in Desmos. Let's see if it matches up with what we just calculated together. We said that this function is increasing from negative infinity to 1. So here's the point at 1, and here's the point at 5. These are my two critical points. Notice that the function has a positive slope all the way up to 1. Then it has negative slopes from 1 to 5, then positive slopes again from 5 to infinity. So increasing and decreasing looks right. My inflection point, which they don't graph for me here, but my inflection point is at 3, and then whatever this function is, so 3f of 3. That's where my inflection point is. So you can see that I'm concave down to the left of that point, concave down, and then I'm concave up to the right of that point, concave up. So it's always a good idea for you to go in after you do each of these examples that we're looking at today and throw the function into Desmos and make sure it matches up with what your diagram is showing you. All right, let's look at another one. What I'd like for you to do is try this out, test it out based on what you think you already know at this point. Here's the function f of x. I want you to tell me which of the following correctly gives the intervals on which this function is concave down. So I want you to go ahead, find the first derivative, find the second derivative, set up a testing map or a sign map, just like we did on the previous problem, and see if you can tell me where the function is concave down. All right, I'll let you pause the video for just a second here, work on it, and then come back and rewatch the rest. All right, if you haven't paused yet, please do so. What we're going to do here is start by taking the first derivative. So the first derivative of this function is 2. And then the derivative of 2 over x, I'm really thinking of 2 over x as being 2x to the negative 1. So that the derivative of that is negative 1 2x to the negative 2, or negative 2 over x squared. So the derivative here is 2 minus 2 over x squared minus 1. The derivative of 1 is 0, so it would be minus 0 here. So the first derivative is 2 minus 2 over x squared. And in this form, you have two things added or subtracted that involve fractions. You cannot tell what the critical points are here very easily. So we're going to set this equal to 0 and solve. My recommendation for these is to get a common denominator and then figure out the critical points. So the common denominator here, this would be 2x squared over x squared, or 2 x squared minus 2 over x squared equals 0. And I'm going to pull out a 2 in the numerator there. And a couple of things I want you to notice here. I want you to notice that x equal to plus and minus 1 are critical points. Okay? That is fine. 0 is not a critical point because the original function is undefined at 0 and the derivative is still undefined at 0. However, 0 is an asymptote. So if you look at the original function, x equal to 0 is a vertical asymptote. Now, you may have worked to this problem incorrectly if you did not include x equals 0 as part of your testing. So it turns out that graphs can change direction at more than just the critical points. They can also change directions at any asymptotes. So when you look at a graph like this one, you have to, on your little diagram that we're going to create here in a second, your testing diagram, you have to put down all of the critical points and any asymptotes, vertical asymptotes that you run across, any places where the original function is undefined. So that's what we're going to do. I'm going to draw in my little testing line here. Before I do that, I need to get the second derivative real quick. So let's do that off to the side here. The second derivative, I'm looking back right here, is the easiest place to take the second derivative from. So the derivative of 2 is 0 minus the derivative of this. I'm thinking of this as 2x to the negative 2. So this will be plus 4 over x cubed. So the second derivative is 4 over x cubed. There are no places where that's equal to 0, so there are no inflection points coming from the second derivative here. So there's no additional points that I have to be aware of and plot. All right, but remember, x equal to 0 is still a point that has to be plotted. And when you plot x equal to 0, you extend the lines as though it affects both the first and second derivative, because it does. This example is going to prove that. Because there's no inflection points here, you might be tempted to think that there are no changes in concavity, but that's not the case. So my critical points are plus and minus 1. My asymptote is 0, so I'm going to plot -1, 0, and 1. -1 is a critical point, so I'm going to extend the region up. Same thing for 1. 0 is an asymptote, so it's going to go both first and second derivative it'll affect. So testing points across the top. So testing like the derivative, let's see, the derivative at -2. So if you plug, I'm looking right here, here's my derivative. If you plug -2 into this, you get 2/4, so 1/2, 2 minus 1/2, that is positive. So I know I'm increasing over here. All right, pick a value between -1 and 0, say like 1/2. If you plug 1/2 into here, 1/2 squared is 1/4. Dividing by 1/4 the same as multiplying by 4. So this is really 2 minus 8 in that case. So at 1/2, -1/2, which makes no difference. At -1/2, this is 2 minus 8, like I said, so it's negative. Notice the symmetry here. If you plug in +1/2, you get the same result. So I know +1/2 will also be negative. So both of these are decreasing. And what I wanted to show you here with this example is the asymptote did not change the increasing or decreasing nature of the function. The function was decreasing before the asymptote. It's still decreasing after the asymptote. Finally, if I test a value to the right of 1, say I test 2, if I plug 2 in, it's the same result as what I had over here. It is once again positive, so we are increasing, which means that we know we have a maximum. We know we have a maximum at -1. There's nothing going on, max or min, because the first derivative test failed. Like, we didn't get a change in the direction here. So this the asymptote at 0, it's not a max or a min. And then over here we have a minimum because we changed from decreasing to increasing. All right, finally looking at the second derivative, we'll calculate the second derivative at each of these critical points. So we'll start with at -1. Here's the second derivative, plug in a -1. -1 cubed is -1, so that derivative is negative, and we are concave down, which is good because that indicates a max by the second derivative test. And then if we look at the second derivative at 1, that turns out to be positive, so we're concave up, which is a minimum by the second derivative test at 1. But this is why it is crucial that you plot this asymptote. If you hadn't have plotted the asymptote on this testing diagram, you would have gotten the first derivative stuff correct because it would have been decreasing everywhere in this interval, except at 0 where it's undefined. But here's where you would have screwed up. Your concavity changed at the asymptote. So you were concave down before the asymptote, you're concave up after the asymptote. What that means is that x equal to 0 acts like an inflection point, even though f double prime of 0 is undefined and f at 0 has an asymptote. So the moral of the story is asymptotes can behave like critical points. They can behave like inflection points in the sense that they can change the increasing and decreasing nature or the concave up and concave down nature of a function. So having said all that and going back to the question that's being asked, what are the intervals on which this function is concave down? Well, I'm concave down over here to the left of 0. So minus infinity to 0 is the correct answer. So if you put B, congratulations, you got it correct. And let's just take a look at that function together real quick. So getting that in Desmos. All right, I think you can all see it. All right, so there's the graph of the function that we just looked at. Make our work a little bit bigger over here. So I'm looking specifically at this testing diagram to see if it fits. We're increasing up to this maximum, which occurs at -1. So we're increasing, then we're decreasing. Increasing, then we're decreasing. So that fits. Once we get to the asymptote, past the asymptote, we're still decreasing until we get to the minimum, and then the minimum occurs at 1, and then past the minimum, we're increasing again. Concavity, we are concave down. This turns down to the left of 0, and this turns up to the right of 0. So all of this fits what we have in our testing diagram. So I think we're in good shape here. All right, so this example was meant to demonstrate how you should handle any asymptotes in the original problem. You should always look for both critical points and asymptotes. So if you have an asymptote, only of the original function, right? Not asymptotes of the derivatives, although oftentimes if you have an asymptote of the original function, it'll stay an asymptote in the derivative. But what I'm telling you to do here is hunt for asymptotes in the original function and then plot those on your testing diagram along with the critical points. That way you won't mess up questions like this. All right, our last example this morning, we're going to try to sketch a graph together from start to finish based on all the information that we've been learning here in this particular lecture. And your book has a very detailed description of how you should approach these sketching problems. In section 4.5, it talks about all the different sort of checklist things that you should do, and I've listed them here, and we're going to kind of go down the checklist and talk about the information relevant to this function. So we're going to start with the fact that this is a cube root, right? So this is the cube root of 2x minus 5 plus 1. That's the function that we're looking at. Now, I should mention a word about domain to start with. So what x values are we allowed to plug in a cube root? This is where pre-calculus comes in handy. You may recall that the cube root is defined for all values of x. So my domain here is minus infinity to infinity. There are no asymptotes. My intercepts, so my intercepts are my x-intercept and my y-intercept. So let's start with the y-intercept. It's usually the easier one to find. So when x is 0, I get the cube root of -5 plus 1. So let me calculate that off to the side real quick here. So that's -0.71 approximately. So there's my y-intercept. And x-intercepts are a little bit tougher. My x-intercepts are places where y is 0, so I'm going to set my function equal to 0. So I'm going to subtract 1 over. Then I'm going to take the cube root of both, or I'm going to cube both sides, right? To undo the cube root, you cube both sides. So if I cube both sides, -1 cubed is still -1. So 2x minus 5 equals -1. 2x equals, let's see, add 5 over, that's 4. So x is 2. So it looks like we have an x-intercept at x equal to 2. Symmetry is where you consider things like even or odd. Our function is neither. So we don't really have any symmetry here at 0. We do have symmetry here if you know basically what a cube root function looks like. There is a little bit of symmetry here at the point 5/2. We'll talk about that point here in just a second. So once you've got these sort of basics out of the way, these are mostly pre-calculus ideas, the A through D here. Once you've determined a little bit of knowledge about the function that you're working with, then comes all the things that we've done in today's lecture. That's E, F, and G. That's finding intervals of increasing, decreasing, local maxes and mins, concave up, concave down, etc. So I'm going to do exactly what we've been doing in class today for this particular example, and that is, let me write down my function real quick. This is 2x minus 5 to the 1/3 plus 1. I need to take its derivative. So I'm looking at doing the derivative tests. So the derivative of this is 1/3 2x minus 5 to the -2/3 times the inner derivative, which is 2, plus the derivative of 1, which is 0. So writing this in a better form, this is 2 divided by, you've got a 3 in the bottom, multiplied by 2x minus 5 to the +2/3 power. So there is my first derivative. Now I'm hunting for critical points, which means I want to set this thing equal to 0 and find any points where the derivative is 0. There are no values of x that make the numerator 0, so there are no critical points, sort of. There actually is a critical point. Remember, the definition of critical point that we looked at last week says a value is a critical point if it's a place where the derivative is 0 or a place where the derivative is undefined but the original function was defined. Remember, the domain of this original function was all values. You can plug any value of x you want into f. But when you look at f prime, if x equals 5/2, then f prime of 5/2 is undefined. So I restricted the domain of my derivative. I cannot plug 2.5 into the derivative because 2 times 2.5 is 5. 5 minus 5 is 0. I produce an asymptote in the bottom. So x equal to 5/2, all this tells me here is that x equal to 5/2 is a critical point by definition, because it's a place where the derivative is undefined but the original function was defined. So I do have a critical point. Let's look at second derivatives now. So if I calculate the second derivative, that's the derivative of the first derivative here. The first derivative is 2/3 2x minus 5 to the -2/3. So if I take the derivative of that, the -2/3 comes down with the 2/3 that's already there. That's -4/9. 2x minus 5 to the subtract 1. So if you subtract 1 from -2/3, you get -5/3. But then I have to do chain rule, so I have to multiply by the inner derivative, which is 2. So this ends up being -8/9 times 2x minus 5 to the 5/3 power. So here's my second derivative. Once again, we see that it has an asymptote at x equal to 2/5, or x equal to 5/2, but it has no inflection points in the top. So it's a critical point by definition and is a potential inflection point. The reason I say potential is we've got to see whether or not this value, x equal to 5/2, changes the concavity. So it's going to be a simple testing diagram here. We're going to put in the point at 5/2, and we're going to test first and second derivative on both sides of this thing. We know that both of these guys are undefined at that point, so I can't put 0 at the top and bottom like I would for a critical point. I know that my first derivative is undefined at 5/2, my second derivative is undefined at 5/2. So let's pick a value to the left. Let's say 1. So if I test at 1, test the first derivative at 1. Let's see, my first derivative's right here. So 2, 1, this is a negative value, but we're squaring it, so it becomes positive. The cube root of anything squared is positive, so this is a positive value. Okay, let's test over here to the right of 2.5, so like say test 3. If you plug 3 into this, 2 times 3 is 6, minus 5 is 1, so that's positive. 2 divided by positive, it's all positive. So I'm still increasing over here. So this thing doesn't act like a critical point because it does not change the direction. This function is increasing everywhere except at 5/2. And at 5/2, its derivative is infinite, right? So it becomes momentarily infinite at 5/2. F prime at 5/2 is infinite. So we get a vertical slope. It's not an asymptote. It's an asymptote of the derivative, but it's a vertical slope on the original function. Okay. If we look at the second derivative, similar thing. So I'm going to test the second derivative at 1. So here's the second derivative. If I plug in 1, I get a negative. This is the 5th power, so it's an odd power, so it keeps the same sign. So if you plug in 1 here, you get a negative in the bottom. You have a negative in the top, so negative divided by negative is a positive. But you can see how this is going to be important because over here at 3, if I test at 3, plug 3 in, you get a 6 minus 5, so you get positive 1 in the denominator. So your denominator is positive. A negative divided by a positive would be negative. And so this is concave down. So this thing does act like an inflection point. We have concave up to the left. We have concave down to the right. So we've just compiled a ton of information. We're going to use the totality of that information to try to sketch a graph. Now there's a couple of points that we're going to be really interested in here. We're interested in what goes on at 5/2. So if I plug 5/2 back into this original function, so here's the original function. If I plug 5/2 into this, that's 0 plus 1. 5/2 and 1 is a really important point along with the x-intercept and y-intercept. So I have a graph down here below, and we're going to try to put all these values in. I know the value at 1 and 2.5, so this value right here is really important. I know my x-intercept is at 2. Whoops, that's not 5/2. It's x equal 5/2 and y equal to 1. That value right there, 5/2, 1. That's a really important value. And then the other value that's important, we had a y-intercept at 2, or excuse me, an x-intercept at 2, and we had a y-intercept at like negative 0.7. Okay, so those are 3 really important values. What I'm doing here is plotting any critical points, inflection points, and intercepts. So I'm plotting those points. I know I have a vertical slope, right? So I have a vertical slope at this point. Right, so I know the graph goes through that point vertically. I know I'm increasing over here, increasing to the right. I know I'm concave up, so I'm kind of curving up through this point all the way to it, and then I'm sort of curving down past it. Now, there are a couple of things you need to know here about ending behavior. So if you take the limit as x goes to infinity of this function, you've got to know in your head what a basic cube root looks like. The cube root looks like if you take x cubed and turn it sideways, that's what the cube root looks like. So you've got to know that this limit at infinity is infinity. If you plug infinite values into a cube root, the cube root of a really large number is also a really large number, and it keeps getting bigger. Likewise, if you go out toward negative infinity, the cube root of a really large negative number is negative, right? The cube root of -1 is -1. So these are very large negative numbers. When you look at limits at infinity, this is what we call ending behavior. So we're looking at the ending behavior of the graph. What does it do out at infinity? So I know that out to the right, this thing goes up to infinity. Out to the left, I know it goes down to negative infinity. So I've got all the relevant information that I need here to kind of finish out my graph. You might want to plot some other points, right? You might want to go over here at -5 and throw that into the function and see what you get. Let me do that real quick here. So I'm just plugging these into Desmos. I know you could go into Desmos and just look at the graph, but we're trying to avoid graphing this thing until or at least till we're done so that we can look at it. All right, so I've got the function put in there, and so let's plot a value at -5. At -5, you're at about -1.4, -1.5. The same thing at true at 5, you're about 1. Actually, I think you're further at 5. At 5, you're at 2.71. So over here at 5, you're about right there. So I have a good idea what this looks like. It's increasing over here. It has to pass through those points. Then it becomes vertical there. Then it levels off and passes through that point on its way out. So this is my best guess at a sketch of this graph. Let's see if we're right based on what we have in Desmos. We'll check it in Desmos. So this is 5/2, 1. This is the 0.20, 0, -0.71. Those values there. So this looks pretty good. I'd be really happy with this sketch if a student gave it to me. So let's test this versus what we see in Desmos. All right, so in Desmos, this is the graph that it gives, and we are pretty close. Point here at 2.5 and 1. We've got our intercept at 2 and 0. Got our y-intercept at 0 and -0.71. So we look good. So we did a good job here. There weren't any maximums or minimums for this example. But if you had any maximums or minimums, you would want to plot those as well, just to make sure that you're correctly putting it in. So what do you plot, right? So think about what you should plot. Points. You should plot your x-intercept. We did. That was 2, 0. Your y-intercept. We did. That was 0, -0.71. Any asymptotes. You should plot those. We did. We knew that the graph went vertical at 5/2 and 1. Any maxes? Well, we would have, but there weren't any. Any minimums? Well, we would have, but there weren't any. Right? These are all the items that you should plot, and then lastly, you should plot any inflection points. And it turns out we did, because the point at 5/2 1 is an inflection point. It's a point where the derivative changes from, where you change from concave up to concave down. So those are the kinds of points that you should be plotting when you're sketching graphs using the tools that we talked about in today's lecture. All right, those are all the examples I have for you. There are many more examples for you to look at, many more functions for you to look at in the textbook and then in the additional videos that I have for you. Hope you all are having a good week out there. I hope everybody enjoyed Easter break. We only got 3 more weeks to go. Hopefully they will go by fast and that you'll all learn the material you need and we'll come out the other end of this thing doing just fine. All right, y'all have a good day. Talk to you later. Bye.